Hello and welcome to our second video on limits and continuity. So today we're going to be doing some more interesting types of problems. Okay, so let's start with this one, another piecewise continuity. So we have a piecewise function f, and is f continuous at x equals 1? Okay, so so you may be tempted to just go like, okay, so limit x approaches 1 minus, right, f of x, we can find that. So that is going to be, so we're approaching from x values that are less than 1. So we're going to be in this piece right here. So we're going to just evaluate at that piece. 1 plus ln 1 is going to be root 5. 1 plus 0, where's root 5? Right, and ln 1 is 0, because e to the 0 is 1. So, okay, and then, right, you check the other limit, plus. Okay, so e to the ln root 5 multiplied by x, and we're plugging in x equals 1. So remember, this is the plus side, so we're looking at x's that are greater than 1. So it's going to be this piece right here. So plug in x equals 1, you just get, right, sort of 1, so it doesn't do anything. And then by log properties, you know, it's just going to be root 5. So, right, we know that x approaches 1, and x is root 5. And so, you may just be like, oh yeah, it is continuous, it looks continuous, you know. But the thing to realize here is you need to know the other condition for continuity, right, which is that f of x also must exist, right? And let's look, does f of 1, right, f of 1, because we're looking at whether it's continuous at x equals 1, does f of 1 exist? Well, no, actually f of 1 isn't even defined, right? We've got it for 0 all the way from the open interval 0 to 1, and then we've got 1 to 2, right? But there is no 1 actually, right? It's not defined at 1. So the answer is just no, it's not. And the reason why this can get tricky sometimes is most of the time, like I'm talking like 90% of the problems that you probably do in class or whatever, will have like a greater than or equal to, like right there or right there. And if this was the case, right, or if this was the function, then f would in fact be continuous at x equals 1 because it's defined there. But as it is in this problem, it's not. So yeah, both f and the limit have to exist in order for continuity to happen. Okay, so absolute value limits. This is one of the more confusing limits that you'll do, and so that's why I chose this one. So in order to do this properly, you need to know the piecewise definition of absolute value of x. So what is the piecewise value? Piecewise definition, it's going to be, so it's basically itself, if it's at least 0, but it's going to be negative of itself if it's less than 0, right? And that makes sense for like what we know the absolute value function to do. Like if we plug in 3, then we're just going to get 3 back, right? Because 3 is positive, and we know that the output of this thing is always going to be positive. If we output 0, right, it's just going to be 0. Same reason. 0 is not exactly negative, so it's fine. It can just be 0. But as soon as we go in and pop in a negative 7 right there, absolute value function can say, no, we have to make that positive. Take the negative of it so that it becomes 7. Right? So that's why we have a minus x here when it's less than 0. Okay, so we can sort of extend this definition to absolute value x minus 2 and sort of rewrite this. And it's going to be defined piecewise as x minus 2, as long as x is at least 2, but it's going to be 2 minus x. Or I'll write this as minus x minus 2, so it's a little more clear. If x is less than 2, right? And this is actually the same thing. Well, why is it, we're just changing it now to 2, because if x is greater than 2, right, maybe it's like 2.1 minus 2, right, then it's some value that's like this value right here is greater than 0. So it is really sort of the same thing, but it's sort of just rewritten to account for this -2 here. We're switching. Okay, so now we know the piecewise thing, so we can better take the limit. So since we know that by limit properties that this limit is going to be equal to this limit approaches to absolute value of x minus 2 over limit approaches to x minus 2, right? I think that we can just go ahead and check this first. Yeah, so basically, since we can split this up into two different limits, we're just going to rewrite this as, like, you know, x minus 2 over x minus 2, as long as we're at least 2, but it's going to be this if x is less than 2. And this is really what our f of x is. So when we write it right like this, right, maybe it's obvious to you that this limit will not exist, because if we're going from the right side, if we're taking x approaches to plus f of x, right, where are the x values that are greater than 2? It's in this piece, so we're going to use that piece, and we're going to get 1, and then limit approaches to minus, right, that's just going to be -1. So these are not the same, so limit x approaches 2 f of x cannot exist. So yeah, basically we rewrote f of x by using this property here. And yeah, we were able to, like, basically combine it because we know that x minus 2 is continuous. But the moral of the story here is to use the piecewise definition of absolute value x to help you out when you evaluate your limit. Okay, so next question here. Functions f, g, and h are continuous. Okay, they're both equal to 4. Don't exactly need this. In fact, I'm going to cross it out real fast. This is kind of redundant, so we only need that part. Okay, so it is known that g of x is less than h of x. Okay, so k is in between g and h inclusive for 1 to 3. Is k continuous? Okay, so what conditions do we have to fulfill in order for k of x to be continuous at x equals 2? Okay, so I've repeated this a lot. I hope this gets hammered in your brain, but k of 2 has to equal the limit as x approaches to k of x, and they both have to exist, right? If we can prove these three things, then we know that k is continuous. Okay, so maybe let's start with k of 2. So how are we going to figure out k of 2? They don't give us k of 2. They don't give us a graph or table of k. How is it supposed to work? Well, we know this. This is what's going to help us. So k of 2, well, for a moment, let's consider g and h, because they happen to surround k. So maybe they'll be useful. So g of 2 has to be, so we know this, right? Because we're just plugging in, sorry, it's a 2. We're just plugging in x equals 2 with that inequality. Okay, but we know what g and h of 2 are. They're both 4. So 4, k of 2, 4. Alright, so this is interesting, right? So 4 is less than or equal to some value, which is less than or equal to 4. So, right, k of 2 has to equal 4. There's no other value of k that will successfully fulfill this inequality. So we know that k of 2 is 4. Great, so now we have to, as long as we can show that and obviously that means that k of 2 also exists. So if we can show that limit x approaches to k of x equals 4, then we're done. And remember, we don't know that k is continuous yet, so we can't just conclude right here and say, oh, k is continuous at x equals 2. We've got to make sure that the limit also is 4. So how are we supposed to take the limit? They don't give us any limits in this whole problem. And this guy also crossed out some other thing that might be useful. Okay, no, it's not useful. But we know that g and h are continuous, so we're going to sort of go the other way. We know that g of 2 is h of 2 is 4, right? And we know that in order for g and h to be continuous, we know that g of 2 had to equal the limit as x approaches to g of x, which also had to equal 4, and a similar logic, we can also apply similar logic to h of x, and that's equal 4. So, okay, we know these two limits, cool. And we also know this inequality, right? So now we're going to apply the squeeze theorem. And I guess I'll just use this problem to introduce the squeeze theorem. If we've got some functions, some continuous functions here that follow this inequality, and if you're taking the limits, let's call this point, let's use 2, right? Normally in the squeeze theorem, you will see, like, just imagine the 2 as like a C or something to represent any point. Plus center equal to limit x approaches to h of x. If we know that, you know, the limit as x approaches to g of x is going to equal h of x, then we know by the squeeze theorem, so write squeeze theorem in shorthand, then we know that it's going to also equal the limit as x approaches to k of x. And for sort of the same reason, the same way that we got to k of 2, right, is because the function k, since it's like it doesn't have anywhere to go but 4, right? Because it's sort of like the other two functions are sort of squeezing in k, right? So like we're talking about 2 4s. Maybe if this is the point, like maybe this is your g, maybe this is your h. I don't know, probably not. But you can have this sort of k right here. Change this color. Okay. You can have this k right here, sort of passing through both of them. So this is k, and then that's g, that's h, right? And so, like, this is why it's called the squeeze theorem. It's sort of like shoved in between g and h to a single point. So, okay, well, what's all this squeeze theorem business about? Well, now we know these two limits, right? Because we knew from the definition of continuity that they both had to be 4. So let's just plug those in. 4 equals limit x approaches to k of x. Oh god, sorry. That should be an x, not a 2. Okay. So, great. We know that the limit as x approaches to k of x equals 4. We know that k of 2 is 4, and 4 does indeed exist, right? So that means that, yes, yes, k is continuous at x equals 4. By the way, if this is an FRQ and you're actually answering this, don't abbreviate like I'm doing, you know, just so it's clear to the AP graders. So yes, k is continuous at x equals 4 because limit x approaches to k of x equals k of 2 equals 4. And we're done, right? And you'd probably get full points as long as you mention the squeeze theorem here and all that. Okay, cool. So find all horizontal asymptotes of f. Okay, so what do we need to do to find the horizontal asymptote of any function f of x? Well, we need to take the limit as x approaches plus n minus infinity, right? Which made sense in the first video, right? If we go back, that's what we did. We sort of we took to the limit as x approaches positive infinity and negative infinity, and we sort of saw that they both arrive at an asymptote y equals f. So with that being said, let's go back to our problem here. Let's try and let's tackle this one at a time, right? Maybe we'll go with positive infinity first. In general, positive infinity is more straightforward, and you'll see why in a second. Okay, so in general, if we were to just, I don't know, let's just take some random limit for now. 4,000 x squared plus x 3x. Okay, so if you were to take this limit, right, you know, like at infinity, anything that's not the biggest term in the polynomial is just not going to matter. So this might be called like dominant term or something like that, but basically you can just sort of like get rid of these and say it's the same as, right, as this. And then you conclude, right, 1/3. Those cancel out. So let's go here. Now, I can use, there's nothing really to do in the numerator, and the denominator, it looks kind of convincing that I could use the dominant term that we were using in this canonical example, but we have a square root. So what do we do? Now, this step might seem a little bit unintuitive, but what we're going to do is we're going to factor out an x squared from that expression. So what is that going to look like? And the reason is, right, square root x squared. We hope to cancel something out. And I'll just write x approaches infinity, right? X squared, this will be 1 plus 1 over x plus 1 over x squared. Okay, and now, right, we're going to use a bit of exponent properties. Rewrite this further. Okay, and next important thing that you may not have learned is square root x squared equals absolute value x. Very important. At least when I took calculus, I did not know this, and I got very confused. Why is this? And the reason is because the domain of any of square root x, right? I mean, sorry, the range of square root x, it's always going to be at least 0. And so that it's sort of like the absolute, it's like x, but always positive. And so that's what the absolute value function is for. So it sort of cancels out, but not really. So, okay, we're going to rewrite this even further. One more time, hopefully. Okay, so we're here now. And this looks a little bit more promising, right? These fractions are going to be nice as we approach infinity, as you'll see in a bit. So, okay, remember, when you're doing this in FRQ, be sure to write the limit as x approaches infinity every time. Okay, now we're here. So now what? So first of all, these absolute value bars are annoying. But what we can do is say, okay, x is approaching positive infinity. So we know that x is going to be positive. So we can just, you know, screw the absolute value bars, because, as you recall from our definition, okay, that was terrible braces. It's just going to be itself, right, if x is at least 0. So, yeah, we're just dropping the absolute value bars there. Okay, we're going to cancel out 2 over root 1 plus da 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 da. Okay, and remember, we're approaching infinity. So what does that mean for this expression here? Well, we've got some nice 1 over x and 1 over x squared. And in general, when you've got like limit x approaches infinity, maybe you've got like a number over some polynomial or something, right? Right, that's going to be 0. right? And the reason is, like, 1 over x, you're sort of getting smaller and smaller and smaller, right? The graph might look like this. Ooh, and it's just going to approach 0. And a similar case for 1 over x squared, or in general, any polynomial. Okay, so that means, right, will approach 0, that will approach 0. So we can rewrite further as 2 over root 1. Okay, and that just simplifies to 2. Okay, whew, right, so that's the limit as x approaches infinity. So we know that there will be a horizontal asymptote at y equals 2. But we're not done yet, right? Remember, we've got to evaluate at positive and negative infinity. So this time I might go a little faster because it's a very similar process, but there's going to be one detail that will change as we go to negative infinity. So actually, I'm going to we were rewriting it basically the same all the way up to right here. So I'm just going to like drag this over. So 2x over absolute value x root 1 plus 1 over x plus 1 over x squared, right? Like all of this was just simplification based on the function. It's going to be exactly the same. So you can sort of like apply the same process here to get to this point if you want. But right here is where it will diverge from what we did earlier. Because, right, when we went to positive infinity, we dropped the absolute value bars because we knew that x was going to be greater than 0. But in this case, we're approaching negative infinity. So that means that x is going to be less than 0. So that means, right, we're going to be using this part of the function. Meaning, right, that absolute value x is now going to be a minus x root 1 plus 1 over x plus 1 over x squared. Right, so now we're going to do the same thing. We're going to cancel. We're going to minus sign out here now. Okay, and then remember, we're x is approaching minus infinity. Now sometimes this, like, even if we're approaching minus infinity, right, it doesn't matter. There's no such thing as a minus 0. It's still just going to be 0. So these two limits will still approach 0. And remember, I'm writing in shorthand form. Do not write in shorthand form on if this is an FRQ. Root 1, and we're going to simplify that to minus 2. Okay, so we know that there will be a horizontal asymptote at y equals minus 2, and we also found y equals 2 earlier. So the horizontal asymptotes will be y equals 2 and y equals minus 2. Ta-da! So, summary, do this if you want to find horizontal asymptotes. Alright, our final problem today is going to be intermediate value theorem. So, what is intermediate value theorem? I'll give you guys a quick explanation. I'm going to try and use less notation because I feel like the notation is just awful. Okay, so so suppose you've got some point right here. Actually, you probably should have, okay, whatever. I'm gonna rewrite this, change this as A and B, this is gonna be C and D. Okay, so this is A comma B, this is C comma D. And more specifically, this would be A, f of A, right? If this is some function, this would be C, f of C. Okay, so we've got 2 points here. And the idea is, if we've got a continuous, I repeat, continuous function, f of x, that passes through these points, A, f of A, and then you've got a C, f of C, right, then f will take on all values in between B and D. So basically, like, maybe there was some value, I don't know, smiley face. And if you wanted to find smiley face, as long as smiley face is in between B and D, right, then you will find a point, maybe I'll call this some point, E is F, comma, smiley face, right? So you will find any value. You can drag the smiley face up and down as long as it's in between B and D inclusive. You will find a point F, comma, smiley face in this, because F is continuous, and in the intuition for this is, right, you can sort of just take 2 points, and like the informal definition of continuity is that you can't like lift your pencil, right? And so you can't lift your pencil at all, so you're forced to sort of take on all the values in between here. Okay, so that's IVT, and the important thing is you've got to check that f of x is continuous in this closed interval. If it's not continuous, then you cannot apply this, because then you can do some sort of all sorts of crazy things where it's like, oh, haha, I don't take this value, and then, you know, IVT doesn't work anymore. Okay, so let's look at this. Question 3. Function f differentiable and g strict. Okay, so what does differentiable mean? So differentiability implies continuity. We'll get to like the more on differentiability later, but basically if you want a Euler diagram, I like Euler diagrams because they're very helpful. This is all the differentiable functions. This is all the continuous functions, right? They're inside. Note that. And so yeah, if you have a sorry, wait, I flipped this. Okay, continuous functions here, and then differentiable functions here. So, right, if you pick some sort of differentiable function, right, f of x, it must be continuous as well. But there might be a function that is continuous but not differentiable. So, yeah. Okay, so differentiability, so we know that f and g are also continuous for all real numbers, g strictly increasing, okay, table above, okay, whatever. Alright, so explain why there must be a value r in this interval such that h of r is minus 5. Okay, so one clue to me that we should use the intermediate value theorem here is that we can find values of h at 1 and 3, right? Because h is basically based on f and g, and I'm going to trust that the table will help me find whatever it is for 1 and 3. And so let's make sure that's the case. Let's find h of 1. So f of g of 1 minus 6. F of, okay, now look at our table. So g of 1 is going to be 2. Okay, and then f of 2 is going to be 9. We know that h of 1 is 3. So now let's find h of 3. Alright, f of g of 3 minus 6. F of, okay, where is g of 3? So, f, okay, so 3 is right here, g of 3, okay, so 4. F of 4 minus 6. Okay, f of 4, sheesh, gotta be careful in these tables. So f of 4 is minus 1. Okay, minus 7, great. So we've got, what have we got? We've got h of 1 is 3, we've got h of 3 is minus 7. Alright, so what do you have to do here? Well, one value where h of r is minus 5. Okay, right, so first thing, check, is h of x continuous in 1, 3? Well, we know that h of x is constructed based on f and g of x, and both f and g of x are differentiable and therefore continuous, so I wouldn't see a reason why f of g of x wouldn't also be continuous. So we know that h of x is continuous also. Okay, great. So now we've met the conditions for intermediate value theorem. So we can say that because minus 7 is less than or equal to minus 5, which is 3, right? Or you can, more precisely, you might want to put in the function here, right? So because this is the case, right, there will be a value, maybe we'll call it C, and then C has to be in between 1 and 3, so such that, right, f of C equals minus 5 by IVT, or intermediate value theorem. So yeah, basically our minus 5 was in between the f values that we were provided, and so since we know that our function h is continuous, we can use IVT to say that there will be a C such that f of C is minus 5. Or in this case, h of r. Sorry, I put f here. This should be h of r, or h of C equals minus 5. Okay, so yeah, that is all we have for today, and I'll see you guys in the next video. Bye.